Okay. All right. So that is the principles of distillation. Okay. Now I'm gonna move on to the next slide. Sorry, the next presentation. A bit long time. Okay. Yeah, up to this one. Okay. Now we're gonna start thinking about the equipment and start talking about a fractionation column. The fractionation column is basically a multi-stage equilibrium. This looks like, okay. Can you see the slide or no?
I think it's still in the presenter view. Yeah.
How about this one?
Yes, ma'am. No, it's
okay. Okay, you can see. All right. Okay, so this is one additional presentation, what a student slide. I took it from the book. This is basically what the outcome of this course. Yeah, the outcome of this course. Well, how to design a distillation column. So this is the outcome. Okay. I'm gonna explain one by one what is this, and we're gonna have a lot of formula or yeah, some of the formula how to calculate. Yeah, but anyway, so it's basically this is an example of distillation of a binary mixture of benzene and toluene, and here we have a feed. Yeah, so this is the feed, and the feed should have a pressure and a temperature. So for this case, the feed is a usually we should specify this feed. The first one is the pressure or the temperature or the phase. Yeah, is it a bubble point liquid or is it a dew point vapor, or is it a mixture of liquid or vapor? What is the ratio? What is the vapor ratio? That is the feed, the pressure, the temperature, or a phase, and also the composition, or we call it ZF. Yeah, we call it Z. Why we call it that, Z or that? Because basically we don't know, is it vapor or liquid, so we just say that. Yeah. Okay, so for this case, and also we have a feed rate or mass rate or a mole rate. For the calculation, we're gonna use everything in mole. So just to make it easier, because the equilibrium it happens in mole. Yeah, all the composition is based on mole. So we're gonna use the mole rate. Okay, so in this case, the feed is a bubble point liquid with a pressure of 55 psi. If you have this requirement, then you can calculate the temperature based on flash calculation. Yeah, remember from the thermo, if you have the phase, or if you have also you have pressure, you have liquid, bubble point liquid, you can calculate the flash temperature, the flash calculation to get the temperature. And also it is a mixture of benzene and toluene, 46 mole percent benzene, and the remaining is toluene. The first compound is the more volatile one. So the benzene is the, I would say this is the A compound, and toluene is the B compound, if you want to make an abbreviation for that one. Okay, and this one, there is a this is the 55 base AA, and then what we see here is the pressure is cooled down with compressor there into like expander, to 19.25 psia, because this is going to be the pressure for the feed. Okay, for in this case, it's a little bit complicated because there is 3 stream for the inlet at 10, at 13, and 16. In this case, this is called the tray. So this is tray number 1. The tray number 1 always on the top, yeah. The tray number 1 always on the top there, and then go down there. So that is the tray number 1, and the lower one is 25. So we're making 25 trays. Yeah, tray. Why is it called tray? Because it looks like tray. Looks like kukusan, yeah, the tray. That trays basically looks like. Okay, and up to here, the vapor is cooled down with a condenser. The condenser is called total condenser. Yeah, the total condenser. Total condenser is a they fully condense all the vapor. So then it has, so all the vapor is totally cooled down using a condenser to become a full liquid, yeah, a saturated liquid. And there is a reflux drum, and then here there is a control to calculate the ratio between the reflux, which is put it back into the fractionation column, and what the other one that left from the fractionation column into the distillate. It's called the distillate. Okay, so here you can calculate which one is the reflux there. So this is the feed to 620 pound mole, and the reflux is around to 6 to 3 as well. Okay, and this is later, this is for the designing of the equipment, one of your oral presentation about teamwork assignment, yeah, about ujian lisan 2. It is we need to also design the tray spacing, the distance between those trays, and also the diameter of the tray. Yeah, the diameter of the tray, and also the type of the tray. It is sieve tray, or it is something else. Okay. At the end of this, all the liquid there is heated up with a partial reboiler. Yeah, with a partial reboiler. Why? Because we need to adjust the condition. With this one, there is a flash calculation as well, where some of them going to the vapor phase and some of them still going into liquid phase. Yeah, and the liquid phase is drained as a bottom product, and the vapor phase going back into the fractionation column as a boil up. For this case, the boil up is 8 pound mole. Okay, and if you think again, there's also the heat duty, how many BTU per hour that we need to have the beban condenser, and also this is a cooling water as well to extract the water, the heat. And this case also we're gonna use steam to boil up them, and this is the pressure about 20.5 psa, and also there is partial reboiler heat duty as well, about 10 million BTU per hour. If you think about it, if you look closely here, the pressure of the reflux drum is 18 psia, and then it's gonna be heated up. And this one is about 20.5 psia. So there's a slight difference of pressure from 18 into 20. Where is the two remaining 2 psaa? It would be a pressure loss or heat or head loss, yeah, head loss in the tray. What looks like what you learned during fluid mechanics, where there would be pressure loss or hilang tekan for that case. Right? So this is not typical this one, but this is what ujian distillasi looks like. Yeah, you have to design up to usually up to the heat duty of the condenser and also to the reboiler. Okay, so what factors that influence the design or the analysis of distillation operation? It include a feed flow rate, a composition, temperature, yeah, like I explained before, the degree separation of between the two components. Do you want a very purity one, 99.99, let's say, or only 95% is fine? It's gonna influence the design of the tray or the how many tray that required. The third one is to the operating pressure. It should be below the critical pressure of the mixture, or if we're talking about essential oil, let's say, usually we put it into vacuum. So the temperature also, if you remember about the PT diagram, if you lower the you lower the pressure, you also lower the temperature, right? So sometimes for essential oil, we need to make it into the vacuum. So the temperature also make it lower. And then pressure drop, yeah. And then there would be, we call it a reflux ratio. There is a minimum one and the actual reflux ratio. The number of equilibrium stages, the number of the tray, and also the number of the tray, the type of condenser, this one, and also the type of reboiler, the degree of subcooling if liquid reflux, the contacting or the tray. I'm gonna explain one by one, yes, so don't worry if you don't understand right now, but I'm gonna explain to you one by one about this, where is the stage, the diameter, and the column internal. Okay, so this is a typical that we're gonna calculate and what we're gonna design. Again, there is a ZF, this one, the mole fraction of a component I, for example. And then for the mole fraction of the distillate, gonna call it XD, yeah. If we have two components, then there's two components. If there's three components, then there's three components. This is bottom, XB. And then this is the feed, yeah. We call it the feed is F. This is also the molar rate of the distillate, we call it P. The molar rate of the bottom, we call it P. Okay. All right. Now, design problem. So like I said before, so what it's known is the feed condition. We should specify the feed condition, or it should be specified in the problem. And also in the distillate composition is also need to be defined. How is the purity the product that we want? Do you want 95%? Do we want 98%? Or do we want 99.9999%? Yeah. Or sometimes bottom product, but usually it's more about distillate composition. And then there is two kind of for bachelor degree, we call it process design, merancang kolom. Yeah, the process design would be we're gonna design the number of the top stage, the tray, or also the number of the bottom stage. For master degree or for master degree, we're gonna move towards problem solving. Problem solving would be looks like, okay, I have a distillation column, but two of the tray is corroded and I have to change it. I don't have money to change it, so I'm gonna just remove it. So what happened to my distillation column? How is the performance? Can I still meet the specified needs? What variable should I adjust so I can still get the product, the purity product that I want, for example? So that is problem solving. This is used by all the process engineer in the field like if they're faced with some problems in their distillation column and how to solve it. Okay, but for bachelor degree, for here for this the third year, we just gonna do the process design and also equipment design, the tray spacing, the space between tray, the configuration, and what is the diameter. Yeah. So for example, designing distillation column, it looks like an architect. Yeah. If you want to design something, it should also need to look good. Yeah, so there is a ratio of the diameter into the length. Yeah, L over D ratio we call it. So there would be L over D ratio. Yeah, I'm gonna explain this one later in the equipment design. Anyway, so don't design distillation column like a pen like this, or don't design with distillation column like this glass. Yeah, buntet, yeah, looks like that. So you need to have a sense of engineers. It's not about calculation. It's all about making a very good shape and aesthetically and also functionality well. Right. Okay. Now we're gonna talk about the mass balance first. Okay. Yeah. We're gonna talk about the mass balance. Let's see, the blue one should be good. Okay. So the mass balance. Let's see this envelope. Okay. This boundary. Okay. So number one is the total one, which is F equal to D, which is leaving the envelope, plus B, right? Okay, for the component, let's say to the component of any component A, let's say that F, multiply with the feed, for example, component A, would be equal to the composition in the distillate, multiply with the distillate, plus the composition of the bottom, multiplied with the molar rate of the bottom product. Okay, so this is the two component, the total and the component mass balance that we know. Okay, now the next one. Okay, now it's very also important how to define the pressure condition. How to define the pressure condition? It is actually based the cooling system of condenser. Think about it. You have a vapor, a very big amount of vapor, maybe like 1 million, or not 1 million, yeah, or maybe 1,000 cubic meter per hour, or 500 cubic meter per hour, and you want to cool it down. So you want to have a cooling system that support a utility system that allows you to have it very economically. Okay, and the most economically utility system for cooling a vapor is using maybe, let's say, cooling water. Okay, you can get the cooling water from the river, for example, if your chemical plant near the river, or from the sea, if your chemical plant is very close to the sea. That's why so many chemical plants near the sea, because we can get unlimited, basically, water, and some of them is used for cooling water. Okay. Now, for the cooling water, let's say this is 25 degrees Celsius. There is a maximum for the cooling water to heat it up. Sometimes it's only like 9 or 10. Correct me if I'm wrong, but you can talk to Pak Harry, Professor Harry, or Pak Walmiki if you want to ask about the utility system, just to remember to, yeah, I need to remember as well, 25 degrees. Okay, so and also then we have also need, because it is counter current reflexible, and would be there is a gap temperature of the heat. So let's say this would be 45, 45, and maybe this one would be, I don't know, maybe 27 or 20, 28, I don't know. Yeah, there would be some pinch point, or maybe 31, let's say. So this is one case. So we need so defining the pressure is actually based on the cooling system of the condenser, because we want a cooling system that is less cost. Yeah, don't use the cooling system that is expensive, except maybe for a for cryogenic application, or I don't know, for vacuum application, that would be something different as well. But maybe some, or maybe the cooling fluid may be, for example, ethylene glycol. Yeah, I don't know. Mana sih? Okay, maybe ethylene glycol or something, I don't know. So, but anyway, the final pressure condition is based on the duty for the cooling system. Yeah, for this one, for the cooling system. Okay. Up to here, any questions? No? You can ask to me now, or maybe tomorrow also. Yeah, try to digest first, and yeah, you can try to digest as well. Okay, anyway, the next one is how to define a product temperature. If the composition of the product and the phase is known, using TXY diagram, we can determine the appropriate product temperature. For example, this one, let's say 0.96. This way, let's say 0.95. Yeah, just saying, yeah. For example, we have a distillate. The distillate is carried out, the distillate is taken out in a vapor phase. What? Yeah. Let's say the configuration of the distillate would be looks like this. So the distillation is a partial. Let's say this is like that. Yeah, we call it a partial condenser. Yeah, so all the vapor there is cooled down, but only half of them is called partial. So sorry, yeah, so the vapor will be as a distillate. So the distillate is in the vapor phase, while the remaining, the reflux, in the liquid phase. So if that, so do we read it? We're gonna read it into the curve for the vapor. This is the curve for the vapor, and we're gonna read it, and this is the temperature for the vapor. Okay, that's number one. Now number two, if the distillation there, if in the total condenser, so we heat it up, so all the vapor there is cooled down, all of them, and then after that to the liquid phase, and then some of them is back as a reflux, and some of them is collected. This case, the XD would be as a liquid. So if this is the composition, then we have to see the graph for the liquid there. Yeah, so this one there, and then this is the temperature for the liquid. Okay, so this is about how to read the product temperature. Any questions?
For me, not yet, ma'am.
Okay, not yet. Okay then. Okay, now let's see the top section first, yeah, the enrichment section. This is a cache for fractionation column. We're gonna start doing analysis of the enrichment using a condenser. The enrichment has n theoretical stage. Okay, first I'm gonna write it here. Yeah, if the condenser is a total condenser, then this gonna be, the condenser would be stage 0. This is gonna be stage 0, and this one gonna be this the top tray gonna be the stage 1. Okay, why? Because in here there is no equilibrium stage. Okay, so if I'm gonna just to repeat again, if the condenser is total condenser, where all the vapor is cooled down into the liquid, that means this is stage 0. Yeah, stage 0, and the first stage would be at the top tray. This is like this. Okay, the second one, if the condenser is partial condenser, it will be looks like this. So yeah, this is the liquid there. So it is vaporized. Some of them is vaporized, and the liquid go back as the reflux. Yeah, this gonna be one stage of condenser. So condenser will be stage 1. Okay, it's gonna be the stage 1, and then the top tray is gonna be the stage 2. Yeah. Okay. I know it's a little bit time to digest. That's fine. Tomorrow I'm gonna repeat it again, or if we have some more example that is more representative, I'm gonna explain it more. Okay, now let's talk about the mass balance. Yeah, so this is the mass balance. So we can see this end flow. So based from the feed and there, yeah, so from the feed, so there up to here. So what we have is the vapor, yeah, vapor at n+1. The vapor n+1 is the vapor from tray n+1, yeah, because the how we write Vn and Ln is the one that is leaving the equilibrium. So for example, this is tray n. So the vapor that is leaving the equilibrium is called Vn, and the liquid that leaving the equilibrium, leaving the tray, is called Ln. Okay, and for this one, the vapor, it came from the tray down just below, so we put it Vn+1. And then would be equal, and then it would be equal into Ln. Yeah, this is the liquid that got out there, Ln, plus over here there is a molar rate of D. Okay, so this is the total mass balance for the enriching section there. Okay, now let's calculate the component mass balance for this case. In here, the Vn+1 should be multiplied with the vapor phase there, with the vapor fraction. This here. Okay, yn+1 multiply with the yn+1 there. That would be equal with the mass balance component for the n there, Ln, and the component balance there. So XD multiplied with T. Okay, so that is the component mass balance. Now, if we divided both sides with Vn plus 1, this would become Yn plus 1, this is divided there. This become L over V, yeah, multiply with Xn, and plus Xd multiply D divided by the Vn plus 1. Okay, so we call this later, it is the operating line for enriching section. Okay, now there is an approach which using McCabe and Thiel, which approach a molar constant over. Yeah.
I have a question.
Yeah. Okay.
I did not quite get what is D again.
D is the molar rate of distillate. D is the molar rate or the molar flow rate of the distillate, that the product that we want.
Okay, thank you,
Yeah.
Miss.
Okay. Okay, now the McCabe-Thiel approach is to put a constant, the approach for the constant molar flow. So what is a constant molar flow? It is assumed, and it also has been checked with the experiments as well. So basically the V here in the tray one, the living tray one, is actually in a quite similar amount with the V living tray two, as well as the V living tray three, because it's basically the liquid and the vapor is mixed together and then separated again like that. Yeah. So it is assumed and also can be approximated constant. So we can change the, instead of between VL V1, V2, V3 for each tray, we can call it V, because it is quite constant, right? Okay, and then for the liquid, it's also quite constant as well, so we can call it L as well. So rather than writing the previous equation is actually sorry. Okay, yn plus 1 equal to L divided by Vn plus 1 xn plus xd dot d over Vn plus 1, and this is also Ln, yeah. If you see again, yeah, this one there. Rather than put that one, we can change this into there. Okay, so so the L and Yn plus 1 would be equal to an equation, L over V. This is going to be a coefficient, and then Xn, and then plus Xd d divided by V. So if we think, if you look at closely about the equation, it looks like a linear equation. Yeah, it looks like a linear equation, and we can see it is y function of x, yeah, x versus y, and the equation is linear, where this is gonna be the coefficient, and this one is the intercept. Yeah, so this become so this is going to be easier, because then we have an operating line. That means if we have an operating line, if we can calculate the operating line here, we can know the correlation between Yn plus 1 and Xn. And if we look at back into the schematic, this is Yn plus 1, this is Xn, yeah. This is yn plus 1. This is xn. So this is so the operating line tells you the correlation between the parallel y and x, yeah, that is changed. One is leaving the tray, one is going into the tray. Yeah, so it show you those correlation. So this is called operating line. Okay, so now your duty is to find operating line, so you can know the correlation between x that going to one tray and the vapor that's leaving that tray. Okay, now my guessing, where is in this sketching is the function of equilibrium. Can you guess where in this sketch is the composition of equilibrium, the correlation of equilibrium? Okay, if you go back to the concept, one tray is actually where the equilibriums happen, right? So you have vapor from down there, and you have liquid from down there, from up there, and they're gonna mix together. And in this mixture together, because of the contact and also the diffusion, there would be equilibrium. There would be equilibrium, and this would be one stage of equilibrium. Okay, and the new composition of the vapor will leaving the tray that way, and the new composition for the liquid with leaving this tray down there, right? Because of the nature, of course. So if we want to draw here, so the correlation for equilibrium would be the one that leaving the tray. So for example, this is tray number 2. The composition for equilibrium would be between this x and y. This is in equilibrium. Yeah. So this green line here would equal to the correlation for the equilibrium. So that's why if you want later on, if you know the equilibrium relationship using y and x, and then you know the composition for equilibrium from the PT diagram or PTXY diagram, and then you know the operating line, then you can calculate how much the equilibrium stage that you need. Okay, I'm going to repeat it again later, but anyway, this is a concept. So you need to understand the concept rather than calculation is fine. Tutorials, how to doing the problem solving for the problems is fine, but you also need to know the concept, and this is the concept. Okay, we have 5 minutes, so I think, yeah, I think we can do that. Okay.
Ma'am?
Yeah.
Sorry, I want to ask
Yes.
for the equation. Yeah, is it the same whether the condenser is total or partial?
Yeah, the same. Because here the envelope, the condenser is inside the envelope, so it doesn't matter if it is total or partial. Yeah, good question. Very good question.
Okay.
Yeah.
Thank you.
Okay. Okay. Good, Ataya. Right. Okay. Now, right. That means we have to know the value of L and also the value of V, right? But the value of L and V is inside the fractionation column, right? And it's also always mixed together. So it is impractical to measure the V or L, right? So we have to find another way to do the measurement. And to that one, we introduce reflux ratio. Okay, reflux ratio is the ratio of the liquid going back into the column divided by the liquid that is leaving the column from the condenser. Okay, so this is L over D. Okay, so reflux ratio is defined as the liquid that going back into the column divided by the liquid that going out the column, or the distillate. Okay, now let's see the mass balance in this envelope. There, this is V. This is going out from this side is L, and this one is D, right? So it's basically, let's say V, the vapor, should be equal to D plus L, or L plus D, yeah? And if we add ratio, we can't really see the green, yeah? So let's see color, maybe magenta. Okay, so if we divide, let's say, divide both sides with V, yeah, this become V divided by V is 1. This become D over V, is it? Yeah, plus L over V, is it? Yeah. Oh no, we need to divide both side with, sorry, we need to divide both sides with R. Don't use this one. Put the eraser there. Don't divide it with, oops. There. Okay, so yes, that's basically we need to divide both side with R. Let's divide both side with L already, both divide by D. So then here we have V divided by D equal to L divided by D plus 1. Yeah, and this one is L over D is R and plus 1. Yeah, so this one there. So, and then with the similar idea too, we can also find L over V there. And also we can find D over V as well. It just to use just to change the equation. Yeah. So from here, for example, we have D over V is R plus 1. So if we just turn it back, it becomes D over V equal to 1 over R plus 1. And what we want there, if you want to check again back to here, here, there is L over V, and also there's also D over V there. So we want to change this. Okay, so we have to, so we know D over V from that previous one, from the ratio, and then we want to also know what is L over V. Okay, so D over V is that, and also L over V would be L, because L is ratio, L over D, yeah, something like that. For L over V, when we do a changing of this, we will get this equal to R divided by R plus 1. Okay, so yeah, so it's exactly L over D divided by V over D. Yeah, L over D is R. V over D is this one, R plus 1. Okay, so this become L over V. So because of that, we can change back into this one there. It's gonna be changed into R divided by R plus 1, and this one is XD R plus 1. Okay, and this one is gonna be our operating line for the top section. Okay. I think it's more than 3 o'clock, so I think that's all for today. Tomorrow we're gonna continue, and then would be hopefully we'll have more comprehensive explanation about distillation. Okay, I'm gonna stop the stairs. So and also the